Okay, welcome to the third video that goes with the second live class of the quantum physics module for Physics 100. We're building up to talking about this paper that has to do with the time spent tunneling. And in the last video, we talked about how to describe the motion of an object like this ball, or a ball bouncing up and down, that in terms of both energy and probability. So the energy constrains the range of places where you can expect to find the ball because it has some fixed total energy, potential energy plus kinetic energy. And when all of the total energy is turned into potential energy at its maximum height, it can't go any higher. So it's bound to return, stop there, fall down to the ground. When it gets to the ground, the total energy it has is not great enough to achieve the amount of potential energy it would need to be inside the ground to burrow its way in there. So it has to stop there, and it's bound between those two areas. If we talk about this in terms of probability, then that means we have a probability distribution, and we find that the probability is very low for it to be found near the ground, because at that point it has a lot of kinetic energy, it's moving rapidly, it doesn't spend much time at that height, and the probability rises to a peak near the peak of the flight of the ball, where it's slowing and coming to a stop. That's where it spends most of its time, that's where it's most likely to be found. So the probability distribution is peaked at the high altitudes. So the question now is, how do we carry this over to quantum mechanics, right? How do we carry this over to something that has to be described in a quantum way that's behaving as both a particle and a wave at the same time? And the answer to that is, well, we're going to have to look at the Schrodinger equation. And what we see from the Schrodinger equation is that the behavior of the wave function is determined by the energy, right? And we know that the wavelength is going to be associated with the kinetic energy specifically. So we can write this expression for conservation of energy, say that the kinetic energy is going to be whatever the total energy of that particle is minus the potential energy. All right. Now we can also say how to relate the kinetic energy to the velocity and more particularly to the momentum. Right. Kinetic energy is 1/2 mv squared in classical physics. And that m and v, that looks a little bit like the momentum. So we could rewrite this in terms of the momentum and say, well, it's 1/2 times the momentum squared, but then you have an extra mass, so we have to divide out another m. So we have that the kinetic energy is 1/2 mv squared divided by m, or it's the momentum squared divided by 2m. Right? And then we can use the relationship from the de Broglie relation for the wavelength to say that this kinetic energy is equal to h bar squared k squared divided by 2m, because the momentum is h bar times k. Right? And that's how it's related to the wavelength. So what does this tell us about the wave function? Well, this tells us that we're going to have a wave function whose wavelength varies depending on the kinetic energy. Right? And if we do a little bit of algebra with this and the definition of k as 2 pi over the wavelength, we find that this wave number k is equal to the square root of 2m over h bar squared times the total energy minus the potential energy. What's that kinetic energy? Okay. What does this mean? This means that if we have a larger kinetic energy in those places, then we expect to see a wave that has a shorter wavelength. So down near the ground, we expect the wavelength associated with this wave function to be short, right? Where the kinetic energy is large, we expect the wavelength to be small. Up near the top, we expect the wavelength to be bigger. So that gives us sort of a qualitative picture of what we expect to see when we make a wave function for something that's behaving like a bouncing ball. There's one question, though, which is what happens in those regions where the potential energy is actually bigger than the total energy of the particle, right? Classically, these are forbidden regions, right? The ball can't go any higher than the point where all of its energy is turned into potential energy, cannot be found anywhere above that, so the probability crashes to 0. Right. Unfortunately, that makes a really sharp peak in the probability. You just can't do that with waves in the same way. We need to find a description of this that's mathematically consistent with what we have in the Schrodinger equation. And that doesn't allow this to instantly go to 0 at those points, right, at the ground or at the maximum height. So the question is, what does happen? Mathematically, it turns out what happens is the wave function in those regions becomes a decaying exponential, right? It looks like some amplitude times e to the minus kappa times x, the position, where kappa is very much like the k wave number that you see up above, but it reverses the v and e. Right, and that's just done so that you end up with a positive real number underneath that square root. So it's kappa is 2m over h bar squared times v minus e, right? The potential energy minus the total energy. And that's what happens in the regions where the potential energy goes higher than the total energy allowed for the particle. So what does this look like in terms of a wave function? Well, we get a wave function that looks like this. And you can see this is doing both particle and wavy things, right? It has sort of the same general trend as the classical one that's still shown in a black line there. That is, the probability increases as we go to larger altitudes because, again, the particle's slowing down. It spends more time in those regions. Therefore, the probability of finding it there has to be higher. We also see that there's wavy stuff happening, and if we look at low altitude, the wavelength is relatively short. That's where it has a lot of kinetic energy. That's where we expect a short wavelength. And the wavelength gets longer as you go to higher altitudes, where the particle's moving more slowly. So this all fits together. And then in this region, gray shaded region at the top, that's the really interesting thing. That's there we see this decaying exponential. Right, we see a probability distribution that doesn't instantly go to zero, but sort of tails off over some distance as you go to this larger region. So there is this region up there, shaded in red, that's higher than the maximum height you ought to be able to reach, but there's still some appreciable probability of finding the particle up there. This is the really interesting thing about this particular wave function for a quantum particle like a bouncing ball, is that there's this region that's classically forbidden, where you shouldn't be able to find the particle, where nevertheless quantum physics tells you there's some probability that it should be there. If there's some probability that it should be there, then it means it has to be there some of the time. So the question is, what can we do to show that this decaying exponential thing is real? That there really is a chance of finding these particles inside these classically forbidden regions, right? What do we have to do that will allow us to show that this is a real physical phenomenon, that this decaying tail actually exists? That is what leads to the phenomenon of tunneling, and that's going to be the next short video in this series, so stay tuned for that.